All right, so just to get started, if you haven't grabbed candy, by all means grab some candy. And take a few minutes and see if you can trace through this. Although after learning from this morning's sections, tracing with 3 takes a really long time, so why don't we do it with 2 instead of 3? So take a few minutes and do that. And for the people coming in, there's candy over there. Help yourself. How do you do this? Trace through it? In most other languages, that wasn't a problem, but it's not right. All right, so you've had a couple minutes then to think about this. And I know the slide says trace factorial of 3. That took like 5 boards. So how about we do factorial of 2? And hopefully you can see whether you're on the right track with 3 or not. So we start out with, a light would be helpful. Light. There we go. So if we do factorial of 2, well, since this is a value, we just substitute that into the body, which is going to be that there. Now those 2 are values as well. And so we end up with I'm going to use ... to represent the rest, just to make this a little bit shorter. And of course, 2 is not equal to 0. So the first question is going to evaluate to false. And so we can get rid of it. And we're left with the else. else always evaluates to true. So in our next line, we just produce the recursive call. And of course, we can't apply this function yet because remember, they need to be values first. So we've got to actually evaluate the arguments first. All right, that's our first bit. Now we're going to call it again. One is not equal to 0. So now we go to evaluate our arguments again. I think you can see why we do condensed traces in the notes, because if we didn't do a condensed trace in the notes, this would take a significant part of your notes. This is going to be our last call because we can see here, now that n is actually going to be 0, we're going to hit our base case. There. So what we've just done here is we've done factorial before, but with simple recursion. And this is doing factorial with a cumulative recursion. And with the cumulative recursion, remember, we're taking a value with us as we go. And the value we're taking with us is the answer so far. So our answer so far is the factorial of the numbers so far. So it's the all the numbers we've seen so far multiplied together. All right, any questions about this trace? All right, so then if you have your clicker, let's turn it on. Now, I know I said I would never ask you a question about proving is something big O of something else. I'm never going to ask you something like that on an exam. But I'm just curious to see, were you paying attention? And if you're having a hard time remembering it, or you're sitting there reciting the definition, going back through your notes, an easier way to think of this is, what is the behavior of 4n plus 3 as n approaches infinity? Does adding 3 to infinity really matter? All right, I'm going to shut this down at 1 minute and 10 seconds. So, all right. Most of you said true. It is true. It is true. And don't worry, everybody gets a point for this. So I'm not going to mark anything wrong here, but it is actually true. Because as n approaches infinity, 4n starts to look a lot like n, and the plus 3 just doesn't matter. And we could do a formal proof of this, but you wouldn't do it in this course. You sure won't do it in CS136. You wouldn't actually be expected to prove this using the definition until CS240. So, yep. No, because as n approaches infinity, it looks very different. And if you actually go then to the definition, you would see that it wouldn't work. However, it is correct to say that n is in big O of n squared. That is true, because the big O, you can consider it as an upper bound as n approaches infinity, whereas n is not an upper bound on n squared. But n squared is an upper bound on n. Yep. Well, if you were so inclined to go about proving this, if you go back to the definition of big O that I actually gave you, you would have to find a constant c such that 4n plus 3 is less than or equal to c times n for all n greater than some number. And if you can find a c and you can find an n and prove that that holds for that c and that n, that's it. You're done. Yeah. Not much to it. This one's fairly easy, by the way. For example, the number 5 for C would be perfectly fine. And I think if you choose n, you could probably choose n as 3. Yeah. They're not too bad. These ones aren't. All right. So, one more then, just to see what you remember about a cumulative recursion. All right, I'm going to stop this here. So, most of you chose A. A is the correct answer here. So technically speaking, you don't actually need a wrapper function for a cumulative recursion. But here's the problem that you would be presented with. With a cumulative recursion, we have an additional argument to our function. That additional argument is the result we've accumulated so far. You would be putting it on your user to know what initial value they should put there in order to use your function. Maybe you need the initial value to be 0, or maybe you need it to be 1. You would be putting it on the user to know that. You would be having to make the assumption that the user read the documentation. Let me tell you a little secret. People don't usually read documentation. It's like those EULAs. Does anyone ever actually read it? No. So, to create user-friendly code, it is beneficial for cumulative recursion to present a wrapper. And the wrapper is going to hide that accumulator from the user. So they don't need to worry about it because they won't even know it exists. So that's kind of fun. All right. So then, a couple of things. Since a number of you have come in the last few minutes, there's a bag of candies over here for Valentine's. Help yourself. You can get up and get one, or somebody can pass them around if you want. Other things is that there's no class next week, right? It's reading week. So if you show up here, and I'm certainly not going to stop you, I will not be here. You're welcome to sit here and stare at the screen. I don't don't care. Preferably, though, you'll go somewhere fun or do something fun. Or, I don't know, like study for, you know, those midterms that are inevitably coming up. I do have a practice midterm for you. It's not quite ready, but it should be ready in the next 24 to 36 hours. I have this thing where if I'm going to release sample problems to you, I also give you the solutions. Because how could you expect to know whether you've done it right if you haven't seen a solution? So it takes me a little bit longer sometimes to actually get them out. So there will be a practice midterm. It will be posted to Piazza probably within the next 36 hours. So you'll have the reading week to actually go through that. I will not be holding office hours next week, but our ISAs will be. And I will be on Piazza though, so if you have any questions, either email or Piazza, that's fine. Yeah? Yes, it is. Yeah, it's the same kind of questions, and I can tell you both the midterm and the practice midterm were both written by me. So that's a pretty good thing. You'll know that the questions are relevant. Now, I have put a warning on the practice midterm that there's more questions on it, then it's a bit longer, but it's just because I want you to have more practice questions to work with. Yeah, but the kinds of questions are the same things that you can expect to see on the actual midterm. So, and hopefully I have on occasion accidentally put a question on the practice that was actually on it. So hopefully I haven't done that. I mean, I know you're all hoping I have done that, but hopefully I haven't. Other than that, make sure you take a look at assignment 5, and hopefully we will have assignment 6 out either tomorrow or early next week. You get a little bit longer to do it. It's also a lot harder of an assignment. But it's short. It's just a little bit harder. I think it's fun. If you like Pokemon, you'll like it. My daughter kept telling me that I had all the Pokemon cards all mixed up, so I don't know. I'll take her word for it. It's based on Pokemon battles. The assignment 6 is going to be mostly just recursion and lists. Yeah. Because we shove recursion down your throat until you it's coming out everywhere. Sorry, that's a gross description. There's going to be 9. I think it's 2 and change. I think our schedule this term only permitted 9 assignments, if memory serves me, so I think we only have 9. If there's 10, I better get on. I'll check. I'm pretty sure there's only 9 though. So, yeah. Sometimes because of the position of the midterm, it changes how things behave. All right. So that's everything then for announcements. So we left off last class, we were looking at a cumulative recursion, which remember that is where instead of computing our answer at the very end, we're taking our answer so far as we go, which is a much more natural human way of thinking, I think. And at the very end of class, we were looking at how to reverse a list, which is a very useful function to have, and we have 2 methods of doing it. So this is just to review, this is the way to do simple recursion. If the list is empty, of course you produce empty because there's nothing to reverse. Otherwise, you are appending the reversed rest of the list onto the list containing the front of this list. That's a little bit backwards to everything you've seen so far, but if we just did Con's first list onto my reversed rest list, then you just get the list out in the forwards order all over again. We want to flip the order, so we can't use Con's because we want a flat list. So we're going to append the results of reversing the rest of the list onto us. It's a little weird to think about, and unfortunately, as with many simple recursive solutions, it's also really slow because append is a recursive function that runs in order n time, and so is my reverse. So you end up with a total runtime of this function as being n squared in the worst case. Now, we can improve it to linear time, which is big O of n, simply by using a cumulative recursion. All we're going to do is, again, we have an accumulator which is going to start out as empty. That's the list reversed so far. And the list reversed so far, well, if you're starting, is empty. And then what we're going to do is when my input list is empty, I produce the accumulator because it has the result in it. Otherwise, we are going to reverse the rest of the list and cons the first of the list onto the reversed remaining of the list. And that does the same thing. And we can actually trace through this. There's a trace on the next slide where you can see we start with the list 1, 2, 3, 4, 5. And then in the next one, we have 2, 3, 4, 5, cons 1 empty. So a list with just 1 in it. And then in the next recursive call, we have list 3, 4, 5, cons 2, list 1. So we're adding the items onto the front, effectively reversing them. This runs in order n times, so it's significantly faster than the simple recursive method. So that's kind of fun. So I wanted to give you a couple other examples of simple recursion. And I know I gave you the suggestion that to get some practice with this, and especially over the reading week, I know you've probably got 4 other courses, but go through Module 8 and Module 7 and find all those other recursion functions we've given you that were simple recursion, convert them all to a cumulative. That's going to get you really familiar with the difference between the two and get you thinking about it a little bit better. So the first one I want to do cumulatively is I want to write a function that determines if an item exists in a list. Effectively, I want to write member. But we're not going to call it that because if we call it that, Racket will complain. But we're going to do it cumulatively. So we have a wrapper. And initially, we haven't found the list or the items, so we're going to produce false. Now, our first attempt at solving this may look like this. We know that if the list is empty, that so far contains the answer. Otherwise, what we're going to do is we are going to check for the item in the rest of the list. And we're going to update our accumulator with, is this current item the item we're looking for? There we go. That works. But here's the thing. Yes, this is an accumulative recursion version member, but we only want to know if it exists in the list. Why would you continue searching a list if it's there? There's no point. You've already found it. So it's slightly more code, but it's a lot more efficient in the long run, or on average, if we say equal so that's a little bit faster. Because if on average we find the item before the first half of the list, we're just going to stop recursing right there. A little bit better. But now we start looking at the use of the accumulator here and we say, wait a minute, this accumulator doesn't actually do anything. And this is actually a really good example of a place where it doesn't really make sense to use cumulative recursion. You can use it, but just because you can doesn't mean you should. You could show up to class in cosplay costume, which is if you do, that's awesome. I don't care. That's great. But maybe you shouldn't show up to an interview like that. So just because you can do something doesn't mean you should. Now, we could modify this function just a teeny tiny bit, and it would make a little more sense to use a cumulative. So instead of maybe checking whether something exists in the list, maybe we want to count the number of times it occurs in the list. And that makes a bit more sense for a cumulative recursion. So we're going to change this just a little bit. where the accumulator starts at a 0 because we haven't found any occurrences of the item. If the list is empty, we return so far because so far is the accumulated result. If we have found the item in the list, instead of producing true, now we're actually going to continue recursing because we're counting how many times it occurs. So we would update the accumulator. Like that. And otherwise, we leave it like that. So this function here, and yes, I know I probably am missing some brackets, is actually a cumulative recursion version of counting how many times something occurs in the list. So you should be able to take all of the functions that you have written in modules 7 and 8 and 9 and convert them into a cumulative recursion. And that would actually be really, really good practice for you. All right. Are there any other questions about how cumulative recursion works? All right. One more kind of recursion then. And it is called generative recursion. So with simple recursion, each recursive call makes exactly one step of progress towards some base case. With a cumulative recursion, it's simple recursion, but now we can take an answer with us. Generative recursion is the wild, wild west. You can do anything you want to any of the arguments. You don't have to make progress towards the base case. It's a free-for-all. Now that might be a weird thing to think about, but here's a math function which some of you may be familiar with that is actually generative recursion. So what it is the greatest common divisor. So we want to know what is the biggest number that divides n and m. And you could do this with simple recursion, by the way, and this is one easy way you could do it. You would compute all of the divisors for n, you compute all the divisors for m, and then you're going to compute the intersection of those divisor lists, and then get the max from it. You can do, it's a lot of helper functions, but you can do that all with simple recursion. It even kind of makes sense. It's not very fast, but it works. But there is this identity that exists, and it might be called Euclid's identity. I don't remember. This course was a long time ago for me. But how it works is we've noticed that the GCD of n and m is equal to the GCD of m and n mod m. And if you do this, it will actually give you the greatest common divisor. So I want to go through an example here, and I really hate using the chalkboard, so I'm actually just going to type all this into Racket. Laziness. So let's suppose we want to do the greatest common divisor of 34 and 101. Because those were, when I made these notes, the first two numbers that popped into my head, not for any particular good reason. So if we take these two numbers here, and what we want to do is we'll start with our first step. That's equal to greatest common divisor of 101 and 34 mod 101. Which is technically equal to the greatest common divisor of 101 and 34. And now we're going to apply it again. So now we have the greatest common divisor of 34 and 101 mod 34, which is equal to, if we simplify it, the greatest common divisor of 34 and 33. If we keep going, now we have 33 and 34 mod 33, which is going to give you, when we simplify it, the greatest common divisor of 33 and 1. Now, any human would be like, oh, the greatest common divisor of 33 and 1 is obviously 1. And we could stop this here. But let's finish to the base case, where m is 0, because that's our base case. When m is 0, the greatest common divisor is n. So now we continue. The GCD of that is equal to 1 and 33 mod 1, which is 1 and 0, and now we get 1. This is a recursive function, but each recursive call does not make exactly one step of progress towards m being 0. It makes some, who knows how many steps towards it. The number of steps, the progress towards our base case is some mathematical function. That's what our generative recursion is. So we could take this very simple code here, and we can actually, oh, that's the wrong one. There we go. We can turn that into a lovely racket function. Wow, it's 2 lines, 3 lines. That's awesome, right? I love this particular feature about scheme and racket, is that there are often a lot of functions that seem really complicated and they end up being like 1 or 2 lines of code. It's great. Not everything. Nobody said it was efficient, but some things can be so simply expressed in this language that it's actually quite beautiful. This is one of them. It's beautiful. It's so simple. So all we're doing is our base case is when m is 0, we produce n. Otherwise, we take the GCD of m and n mod m. That's it. Done. So with our generative recursion, as I said, the thing we are recursing on, we may actually be recursing on more than one thing, but the steps towards the base case is some function. Now you might be wondering, what are some other examples of generative recursion? What if I wanted to do counting down from a number by 2s? Now you might be thinking that's simple recursion. Well, that's not going to work because maybe we're doing odd numbers. So we have this function here. And it looks so much like simple recursion, but it's not. It's generative recursion because we are not moving one position towards our base case, we're moving 2. The progress towards the base case is not simple. We can run this if we so chose. Always helps not to have typos. There we go. This is generative recursion, not simple, because again, the progress towards the base case is a function, not a simple rest or n-1 or n+1. Now, we introduced you to this idea of generative recursion, which is really wonky and it can do whatever you want it to do, but we're not really going to use it. We're going to avoid it for now. We will revisit generative recursion at a later date, but it's important that you see this so that you know how it is different from a cumulative and you know how it is different from simple. Yep. Well, I haven't really considered the base case too carefully. All right. So just to go over all 3 kinds of recursion you've seen so far, you've got simple recursion. That is that every argument either does not change or makes exactly one step of progress towards some base case. A cumulative recursion is the same, but it adds the ability to have an accumulator which holds the results so far, so that is changing. Yeah? Yep. That's simple. I know. You're sitting there shaking your head like, what? It doesn't seem any different. In a lot of cases, simple recursion and generative recursion, they kind of seem like the same thing. I want to say it's all just a bunch of labels, and I like to call all of this stuff just recursion. All right. So cumulative recursion, again, we've got that extra parameter that does change, but it's just our result so far. And then generative recursion is that all parameters, there can be as many as you want, and they're calculated however you want with each step. It's a free-for-all, which is why it tends to be a bit messy. All right, any other questions about recursion then? Yeah?
Would you say that cumulative recursion is part of generative?
I mean, maybe you could argue that cumulative recursion is a part of generative recursion, but at the same time, the arguments to a cumulative recursion, we're still very clearly defining their behavior. They're either not changing, moving one step closer to the base case, and that's the key, one step closer to base, or storing the result so far. Whereas with generative recursion, the arguments can have any kind of calculations whatsoever. Again, this is where the labels of recursion maybe aren't so great, because I think you probably could argue that cumulative is maybe a sub-case of generative. But we're going to consider it just separate. I'm not going to get into the labels of recursion debate. All right. So now that you have had like 2 weeks of recursion such that it's probably like bleeding out of your ears, how about something different? Like not recursion. And I know you're sitting there, loops? No. Not loops. So here's the thing. We've been working in the last few weeks with something we call compound data. That's what a list is. It's a compound data type. It's a data type that actually can contain many other data types. It can even contain other lists. And we've used lists to represent all kinds of different types of data. So we've used lists to represent students, where a student has a name and a program and a list of classes you're currently enrolled in. And if you remember some of the previous assignments, we've used a list to represent a color, where the first element of the list was the red component, the second element of the list was the green component, and the third element of the list was the blue component. And we've used it to represent a sphere, where the first element of the list was another list that had 3 elements, that was the center point, and then the second element of the list was the radius. So we can actually use these lists to represent all kinds of different data types. But here's the thing. Anytime you wanted to access one of those pieces of data inside the list, you were restricted to kind of using functions like first and rest, and first of the first, and second of the rest, and so on and so forth. And those functions, first and rest, when you're trying to access, say, the radius, if I'm going to say the first of the rest of the list, that doesn't tell me, the reader, that I'm getting the radius out of the sphere. So it wasn't very helpful. They're not very user-friendly ways of accessing the data inside of these different lists. What you really want to do is you should always be trying to provide your users with the most friendly way to access data. You should never assume that they can decode first of the first. It's just as bad as having a bunch of coulders and cadadders and all of those things from the old scheme. So what you want to give your users is a nice wrapper function. So you want to get the center point of the sphere, you would make a function called getSphereCenter. You pass it that list, it produces the center point. You want to get the radius of the sphere, so you create a wrapper function that's going to give you the second element of the sphere, which is the radius. when you create those wrappers for those different elements of the list, you just made your code more readable. Yes, I know you just wrote more code, but you gave your user an overall better experience, and then when you're implementing functions on spheres at a later point, instead of trying to remember, now what was that data definition for a sphere? And then you got to scroll back to the top of the file. Oh yeah, and then by the time you scroll back down, you forgot it again. And so you can't remember what's the rest? I don't remember. No, you create these wrapper functions not just for your users, but for you to use later so that your code for you is super readable. So let's actually do that. So what we want to do is we're going to use a student example because you're all students here. And what we're going to do is our student has 3 parts: a name, a program, and a list of classes you're enrolled in right now. So 3-element list. And what I want to do is I want to create a bunch of wrapper functions to give to the user and to myself so that I can more easily use this data type throughout my code, to make my code more readable. And you want to know something else you get out of this? You actually give code that's more maintainable and more reusable because you've hidden the list nature of the student from your user. So if you go back and you change a student to have more fields, more entries in the list, since your user was always using your wrapper functions, they don't need to know what the student actually looks like. They only need to know how to access the things inside. So we're going to make a bunch of functions then. One function we're going to make is a constructor. We pass all of the bits we want to create the student out of, like their name and their program, and it's going to give us a list that has the correct format of a student. And then we want to have a predicate to check, is the thing you've given me a student or not? Is it a list with a name, a program, and a list of classes? I want to know that. And then a bunch of things to actually access the name, access the program, and access the classes. So we're going to start with this rather curious looking data definition. Our data definition says a student is a make student stir list of stir. That's really weird. But what that actually is the constructor. So let's go down here. This is our constructor for our student. And what this constructor does is it takes a name and a program and a list of classes, and it's going to create the list that we're using to represent the student. And once we've created this lovely constructor function, we can actually use the constructor in our data definition. Isn't that awesome? It's pretty cool, isn't it? Now, you might be wondering, I thought you said that a student only has 3 elements, a name, a program, and a list of classes you're enrolled in. What is the student tag? So here's the thing. I want to be able to differentiate between somebody trying to use student functions on a list containing 3 elements and an actual student list. So I need some unique way of identifying this is a student that I created with the student constructor from any other list that somebody made. So what we can do is we can create a unique code. And it could be a string, and it could be a number. Users shouldn't know what it is. And what we're going to do is we're going to stuff that unique code into the list. And now my student is uniquely identified as this is my special student created with this constructor. We can now create a predicate to indicate is this or is this not a student. The downside of using this unique code in the list is that we must now absolutely provide our users with functions to access the name and the program and the class list, because if we don't, they're going to be able to get this unique code out, and we really don't want them to know about it. So now we actually need to create those accessing functions. All right, so let's create that predicate then. So a student, there are several things that are true. A student is actually a list, and that list should have 4 things in it. And the first element of the list should be that unique code. So I'm going to check to make sure all three of those things are true. So we are a list, our length is 4, and the first thing in the list is that tag. If all three of those things are true, we are going to assume that you are a student and we will produce true. If any one of those things is false, we're going to produce false, that this is not a student. Now, how could we improve this function? We shouldn't get rid of const, because what if somebody passes the number 4 in? Number 4 is not a list. I can't call length on it. The thing I want to get rid of here is actually the number 4. Here's the problem. My definition of a student right now is a list of 4 elements. But what if I change my definition of a student? And now it has 6 elements in it. You're telling me I'm going to have to go back to this function, modify it, to change that magic number? I don't want to do that. That makes this difficult to maintain. So for maintainability purposes, I would actually create a constant to represent how many elements are actually in the student list. There's one other thing I would do. Right now, we have hard-coded the fact that the special identifying token is in the first element of the list. What if I decide at a later point to store it in the nth element of the list instead? I would have to come back and change this code here. So we could generalize this by keeping another constant that indicated at what position in the list can I find the tag, and then modify this code so that it checks that specific position for the tag. And if you do those two things, you have a beautifully maintainable and generalized predicate function for students. Now, you might be wondering, I have no idea how she came up with those things. That's okay. This is something that takes time. So don't expect to see the most general or reusable solutions right up front. And I know I keep reiterating that, but I don't want you to think, I couldn't see the answer here, I must be doing bad. You're not doing bad. You're new. That's okay. All right. So we've got our constructor, we've got a data definition, we've got a predicate to check if this is a student. Now we need to have some functions to actually extract the name, the program, and the class list. So this function, the accessor or selector, however you want to call it, is going to, we call it student name. And we want to make sure before we just extract the first of the list, or the second of the list in this case, we want to make sure this is actually a student you've passed me. I shouldn't be trying to get the name from something that isn't actually a real student. So what we're going to do with all of these functions is validate first that this is a student using the predicate that we just created. Once we validated it's a student, then we will actually produce the second of the list, which is going to be where our name is stored. And then if it's not a student, we produce an error. And this is one of those rare cases where we'll have to use check error to make sure that when we pass a non-student through this function, we actually get the appropriate error message. Now they haven't given you the functions for program and the function for class, but we can do one of them real quick, and you'll see it's the same format quite literally. So all we want to do then is we would just do, let's get the student class. That's it. So the format, the template of these selector functions to get certain elements from our student data type is roughly the same for each of the elements. We're just going to change which element we're actually trying to access. So if I asked you then to create this constructor and all of these selectors and this predicate, for most most of the data types you've seen so far wouldn't actually be that bad. For a sphere, sphere only has a center and a radius. For a color, it only has a red, a green, and a blue value. But what if I had a data type called lotto picks, and it has 10 fields. There are 10 entries in the list, and each of those entries is one of my lotto numbers. So, how many functions do I have to create? I have to create the constructor, the predicate, and 10 selectors. So that's 12 functions in total I need to create, and on top of creating those 12 lovely functions, I have to create the design recipe for them. So, contract, examples, tests. It's a lot of work. It's a lot of work that you didn't actually have to do. Because Racket can actually do all this work for you. All of it. And that's kind of cool. And it's called structure. There's a magical function in Racket called define struct. And what it does is it's letting you specify the format of a data type. And so if I want to create a structure for my student, I say define struct, I pass it the name. And then in brackets, I pass the names of each of the fields contained in my student. I don't say what types they are, I just give them names. And after I put that one line, define struct, do you know what Racket gives me for free? The constructor, the predicate, and all of the selectors get built for you. Now the question is, do you actually believe me? So let's actually go do this. So we'll go over here. Got some nice empty space. So let's define struct a color which has 3 components, a red value, a green value, and a blue value. Okay, you'll note the only thing I have done is put define struct there. And now I'm going to get a whole bunch of functions made for me. So I get a constructor. I also get a predicate. And if I pass to the predicate something that is not a color, let's say I pass it a list of 3 things, you'll see that it doesn't turn out true. It turns out false. And I also get selectors. And I get one for green, and I get one for blue as well. All I had to do is type define struct. And all of those functions we just took so much time writing, Racket gives you for free. So, when I create this student structure, it's going to give me the constructor, the predicate, and 3 selectors. One for the name, one for the program, and one for the classes. You get them for free, which means you don't have to do the design recipe for any of them. They're effectively built in. You do, however, still need a data definition. The nice thing about the data definition for a structure is we just say a student is called a constructor. Except for all of the arguments of the constructor, you're going to specify the types. You're done. There's your data definition. Easy. Now, I'd like to show you the general form of using define struct. So the general form looks like this. That is the general form of creating a structure in Racket. And then the form of all of the functions Racket gives to you will be where each of the field i's are args to the constructor. So I'll actually write that in there. And then we're going to get a predicate. That looks like that. And then you get selectors. And the selectors have the following form. That's it. You get all that for free. Yeah. Yep. No, you don't need the student tag because it's going to do that for you. Because that tag should never be exposed to the user. Because if the user has access to that unique tag that identifies it as being a student, then I can fake it. We don't want to be able to fake it. So that kind of thing is hidden from you. You don't even to know it exists. All right. Any questions about how we do this? Yep. If you wanted to, there's nothing stopping you from but it would be a field. So it would be a field, but you would have to make sure that every time you call the constructor, you pass the same value into that field. No, you can't build it into the constructor. No. If you had something where you wanted to put a constant tag in each of your structures, then you should use the previous method and actually do it all yourself. But yeah, this is letting Bracket handle that tag for you. All right, any other questions about this? All right. So, now, we could actually use this. We could go out and we've created our structure, we've created our data definition for it, and now we can start writing functions. The really beautiful thing about define struct is you're not going to be spending time actually writing the functions to construct and select the different fields. You are going to be spending time writing the actual functions that matter. So things like maybe you decide you want to add a sixth class because I'm not sure why anyone would do that, but maybe you decided you want to. So we could do that. We could do a function called add class, and it consumes a student and a class, which is a string, and it's going to produce a new student. Now, something to remind you of is that Bracket doesn't let us modify existing things. We always have to produce a new value. So when we had a class, we pass in a student, and we actually get out a new student structure where the name and the program are the same, but the class list is different to reflect the change that we made to it. They are two separate things. What happens to the old copy of you really depends on context. So what we're going to do in add class is we actually call the constructor. We get the name of the student to put in, program name, and then we add the class to the classes we get from that student, and that's it. The other really nice thing about these functions that Bracket's provided to you is it makes your code more readable. If I want to get the name of the student, there's no more first of the first, or remembering that the program is the second thing, or that the class list is the second of the rest of the list. We don't have to remember that because we have these beautiful selector functions that are clearly named, that there's no other meaning they could possibly have. These functions are really, really great, and they make really readable code. So again, here's just the general syntax of it. I've already gone over it, so I'm not going to spend too long on this particular slide. But now that you have the general syntax of it, you might be interested in knowing how do you actually do stepping and tracing with these lovely things. Actually, there's not much to worry about. So first off, we're going to note that if you see the constructor, and each of the arguments to the constructor are values, not expressions, then that whole line is considered a value and no substitution is required. that there make name with values, that's considered the structure. That's a value. If you see the selector, and the selector is passed a value, i.e. a structure, then you just produce the field that the selector was trying to access. One substitution step. These are built-in functions, so you actually don't know how they're implemented. The predicate behaves much the same way. If you pass the predicate a value and it is of that type, then it produces true. If you pass the predicate something else, it should produce false. They are built-in functions. You don't know their implementations, so you don't have to worry about any additional steps. Each of these evaluates in one. And this actually points out one of the beautiful things about using brackets built in defined struct, is that you don't need to worry about how Racket is actually implementing it. They have abstracted the implementation of this away from you such that the user doesn't need to know if lists are being used underneath or if something else is being used underneath. And in fact, Racket could change it and you would never know, because the implementation has been abstracted away from you. They provide you with an interface, just a bunch of functions. They tell you how to use them and what, and that's it. You just make the assumption they work. You don't care how they work. It's like that Aphrodite app I see all over Reddit right now. You don't care how it got you a match. You just care it did. Although all the posts right now seem to say that nobody's getting them, or maybe I'm just not reading them too well. Sounds like fun. So you created a student using the constructor. So then they can just, so if you created a student at the very top of your code and they want to call the student predicate later on, that's fine. No, you only have to create it once. So you only need to use the define struct once. And then each time you create a student, if you're creating it as a constant, you just define your name, make student, there it is. It's a constant, lives forever. That's exactly right. Once you've defined it once, it's around forever, so you can just use that predicate and it's, it's there. So these functions don't disappear. Once you use that defined struct, they're there forever. Well, at least they're forever in that file. Yeah. You cannot define two predicates with the same name. In Racket, you cannot have two functions with the same name. I won't actually let you. Some languages will let you have multiple functions with the same name, but they have to take a different number of arguments or produce a different type. Things like C++, you can do that. And Java, and things like that. All right. So, one more thing you do have to do. So you are required to use the define struct to actually, make the structure, and so that Racket will know to make all those helper functions. And you have to, with define struct, you must always also give the data definition. But since you can use the constructor in it, it's usually a one-liner, so that's nice. You still have to make a template, though. Beautiful thing about the template for a structure, though, it's real simple. So in this case here, this would be a totally defined template. So your template should simply show you accessing each of the fields of that particular structure. So you've got three fields here. We've got a name, we've got a program, and we've got a list of classes. So in our template, we're accessing the name, we're accessing the program, and we're accessing the classes. That's it. Now you've got a template. And in fact, that would be the general form of our template. We can do that too. So our general form of the template would be There you go. There's the general form of the template function for a structure. And now you can create any structure you want, and you can fill it in with this template here, and there you go. Yep. So if you use define struct, you do have to use you have to give a template. So anytime you create a data definition or a structure, you have to create a template for that thing. Yes, you have to give a contract for this as well. Not the full design recipe because it's not a real function, it's a template. So you can't actually fill it all in. You have a question?
Yeah. So you comment that template out?
You actually don't have to comment the template out in Racket. And the reason is, so this is built on a teaching language, so it's kind of familiar with this, but the other thing is so long as you don't actually try to use it, it will never actually get evaluated. So for example, we should be able to run this, and of course I have some other things in here which are causing it to crash, but let's just comment that one. I'm going to comment a few of these out because they are going to cause a crash. But as you can see here, I've just run with this template, no problem. It's kind of cool. Now, I wouldn't go and do this in Scheme because I don't think Scheme would like you very much. But inside Dr. Racket, this is fine, so don't worry about it. All right, so that's fun. Now, maybe I want to have a list of students. So we have an individual student structure. What if I want to have a list of structures? Well, guess what? You can do that because lists can contain anything, and there's no reason why we can't have a list of structures. And guess what? Recursion is going to look exactly the same. Recursion generally doesn't change because you change the contents of the list. So we want to create a list of students. Let's say it's the list of all the people in this room right now. So there's a number of things I might want to do. Number one, I usually like to see my students in alphabetical order. I don't know why. That's just one of those standard things. So I may want to be able to produce the list of names of everybody in the room. I may want to be able to add students. Maybe a whole pile of CS145 students decide they want to come down to 135. Because why break your back for no reason, right? So we've got a bunch of 145 students I now need to add. And I want the ability to add the 145 students in alphabetical order to maintain that alphabetical ordering of my class list. Or I may want to remove students. On that note, the drop-down deadline for CS115 is tomorrow. So if you are deciding that this is way too hard, dude, just go to 115. And by the way, on that note, I was supposed to mention this earlier. If you drop down to 115, it's a clean start. So your marks from 135 don't go with you. Yeah, it's crazy, right? So, on that note, let's suppose a bunch of you decide to drop down. And again, no judging. If that's what you need to do, by all means do it. So we want the ability to remove some of you from the class list. So we'd want to make sure that after we've removed a bunch of students from the list, that it maintains that alphabetical order. We may also want to make sure that everybody that I believe is in this class also believes that they are in this class. Because it would be really weird if this was a course and I thought you were in it, but you weren't, and then I put an exam out for you at the end of the year and you don't show up because you didn't actually enroll in the course because Quest screwed up, and you get a 0 in a course you never enrolled in. That would really suck, right? So we want to validate that everybody that I think is in my class has actually enrolled in the class. So we've got a bunch of functions that we could do here. And so once at the top of my program, I will create the definition for the structure. I'll put the data definition. I'll put the template for the structure as well. And then I'm going to have a data definition for a class list. And now I just say class list is a list of students. You should also, because you've made a data definition, you should be giving a template here. I'm not going to put the template. They haven't put the template. It's the standard simple recursion for a list template. So then I'm going to make a bunch of students. And now what I'm going to do is actually try to write some of these functions. And all we're trying to point out here is that when you have a list of structures, it's the same as having a list of anything. The recursion is going to look the same, but how we actually deal with the individual elements of the list is going to change just a teeny bit to make use of the selector functions. So for example, if I want to produce a list of the names of everybody in the room, I'm going to consume a class list. If the class list is empty, I produce empty, because I'm getting a list of names. Otherwise, I cons the name. We're using the selector here because this is a list of structures, the name of the first student onto the names from everybody else. Same thing, but now instead of just using the first of the list, the first of the list is the student structure that we're applying the selector to. All right. Then we have, what if I want to add students and make sure they're being added in alphabetical order, so making sure that the order is preserved? Well, actually, if you look at this function, it's actually just insert from insertion sort. So all I'm going to do is I'm going to compare the name of the student I'm trying to add to the name of the student at the front of the class list. And if my student I'm adding, their name would come before alphabetically the student at the front of the list, then I cons the student onto the front of the class list. Otherwise, I'm going to try to insert the student into the rest of the list. So it's literally just insert from the previous module, change to work on strings and structures. Same recursive format, slightly different things that we do with the actual list elements. The last one, of course, is validating that all of the students that are in this class actually are truly enrolled. So we want to check to make sure that every single one of you actually has CS135 in your list of enrolled classes. So we want to know if 135 is a member of your class list. And we're going to do that for every student. So if the class list is empty, we produce true because there's no students. Therefore, there's no problems, right? Otherwise, we're going to and checking the current students with checking the rest of the students. And again, note that instead we're using first to access the student in the list of students. But once we're trying to access the fields of the student, we use the selector for that particular field. All right, any questions about this? Nothing particularly new here. All right. Now here's the problem with what we've just done. Student is a very general term. There are many different kinds of students here. We could look at things as domestic versus international students. It's one totally valid way of doing it. But you know what? Here's a better way of doing it. There are undergrad students and there are grad students. And there are some pretty big differences between a student record for an undergrad student and a student record for a grad student. An undergrad student has a name and a program and a list of enrolled classes. A grad student, yes, they have a name and they have a program. They could have a list of enrolled classes, but grad students don't take a lot of classes. But they also have a supervisor. They can even have more than one supervisor, and they have funding. So, our definition of a grad student and our definition of an undergrad student are very different. And yet, we have undergrad and grad students often taking the same courses. So for example, we often have grad students coming in from non-computer science areas, and the school believes that you need a little bit of a background in CS before you finish your degree. So they ask some incoming grad students to take CS350, which is operating systems, and CS341, which is algorithms. That gives you a pretty good foundation. And so those courses, we often have both grad and undergrad students. Now, because those two kinds of students have different kinds of fields, how are we actually going to work with that? Now, if you're sitting there, I know how to do this in Java, I'll make a student class, and I'll have an undergrad, they'll inherit from student, and I'll have a grad student, they'll inherit from student, or in your C++. Yeah, we don't have that in Racket. That's called polymorphism, by the way. That's CS246. We don't have it in Racket. So what we're going to have to do to deal with this mixed data is, instead of creating a student structure, we are going to create a structure for each of the types of students. So I'll create one structure for an undergrad, and I'll create one structure for a grad student. And then, because I want to classify both of these as students, I will create a data definition, not a structure, for a student. So a student is one of an undergrad or a grad. But that is not a structure. Then I will create a data definition for a class list. And then I've got to create a template. But the template's going to be a little bit different now, because students may be undergrad or grad students. And depending on which type of student you are, it's going to change which selectors I have available to me. So my template is going to have to check whether you're a grad or an undergrad. And if you're a grad student, it'll have the selectors for the grad student. And if you're an undergrad, the template will have the selectors for the undergrad. So my template for student looks like this. We've essentially just combined the template for undergrads with the templates for grad. And now that we have this, well, because student isn't actually a structure, it's just a data definition we created, we don't get a constructor for free. And we don't get any lovely other functions for free. So I would then have to go out and I would have to manually make any functions that I think are required for students. So for example, if I wanted to update a student's program, maybe that's going to happen. Maybe you're in the environment program and you're going to come join us in the dark side of CS. We need to update your program. So in order to do that, we would have to actually check whether you're an undergrad or grad student, because maybe you're a grad student that decided, you know, trees, they're just not for me. I want to go write code. So in our update program, we're going to check whether you're an undergrad or grad, and then depending on which one you are, we're going to create a new student structure using the constructor and modifying the program. And that's it for mixed data. It's not too bad. And there's more functions we can create. So we can filter a class list based on program. Any kind of function that we're going to do, though, we're going to have to make sure that we're treating undergrad students differently from grad students. Because remember, they are two different types of structures, so the selectors to access their fields will be different. All right, I'm going to leave that there for today. We will finish up with structures like 10 days from now or something. I'm sure you will have all forgotten it by then. So we'll do lots of examples when we return. Don't come here next week. Seriously. I'm not going to be having office hours, so don't. Candy. Go eat candy.